بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone. Today, inshallah, some good news. This is the last lecture on the dynamics part. So last lecture on the topic number 2. So next week, inshallah, we're beginning with the lecture topic number 3 on fixed base manipulators. Just as a recap of what we were doing here, everything we were discussing in this part is writing the equations of motion, the dynamic equations, the governing differential equations that say how a rigid body that's just thrown out there in space, how it's rotating and translating, and how are these coupled together. The main conclusion is that translation and rotation are not two separate things, right? So it's both of them are one entity. They are coupled together. Rotation, when you have rotation, it affects how you translate. And of course, when we start talking about forces and torques, again, you start getting all of these issues in terms of wrenches, and this we're going to be discussing today. And this intuition, you always have it all the time. For example, whenever you talk about a force at a distance, then what does this cause? A torque, right? So you're all familiar with this idea that there's no such thing as like a torque, or you can do rotational dynamics and discuss about torques without talking about forces, right? Depending on which frame you're looking at or which point you're considering this apply to, you get all of this combination. So this is the main goal of this part. And what was our approach to model rigid body dynamics was based on the Lie group approach, using the fact that SE3, which is the configuration space of this rigid body that's floating out there, has this Lie group structure, has this geometric approach, and this is how we connected topic 1 and topic 2. Recap of last lecture where we did the dynamics. So last week we were done with the kinematics part, which is describing how velocities affect, how are they related to the rate of change of pose. And now we have these 3 cases where you have just a point mass with no orientation that's translating. You have a rigid body rotation, and you have a rigid body motion, which is a combination of translation and rotation at the same time. And our approach was to start from the kinetic energy, and then we introduces the force. For example, in the case of the point mass, we only have velocities and forces. The kinetic energy is half mv squared, but written in a vector format. The momentum was the gradient of this kinetic energy with respect to the velocity, which is what you know as mv. And Newton's law is simply the rate of change of momentum is equal to the total forces applied on this point mass under the condition that you're expressing everything in a stationary frame, a frame that's not moving. And then you reach the equation that you're all familiar with, which is, acceleration is equal to force divided by mass. And this was the picture that we started with. This should be familiar to you, where you have the forces, and they're equal to the rate of change of the momentum. The momentum we can integrate, and then we can multiply by the inverse of the mass or the inverse of the inertia. We get the velocity, and then the velocity is same as the rate of change of the position, and the position we integrate, in Rn in the usual way. And these are the equations that you're all familiar with. You can take these equations written in terms of the position and the momentum, and you can write them in terms of position and velocity by just eliminating the momentum equation, or simply by eliminating the velocity equation. You can have a second order differential equation in terms of the position. So this should be familiar to you. Going from positions to rotations, things get a little bit nasty. We introduce the torques, which are elements, which are, again, it's a 3-vector that applies in 3 directions, some sort of torque, or like this moment that generates this motion. And then we have the kinetic energy, which is also half omega transpose j omega. But now the j depends on which frame you're looking at. The j can be a function of the rotation matrix or not in general. And we define the momentum, the angular momentum, in the same way by taking the gradient of this kinetic energy with respect to the velocity, giving us simply this j omega. But again, it can be dependent on the rotation matrix or not. And Euler's law, again, states that the rate of change of angular momentum is equal to the total applied torques on this rotating body, provided you're looking at a stationary frame. And we said that we're not interested usually in the stationary frame, because when we do that, we get a coupling actually between the momentum dynamics and the rotational dynamics. Because when we're working here with the J, and the J depends on the R, the equations they don't become nice. So what we try to do is usually write the momentum in the body frame. And then what we saw last time is that we can express this momentum balance in the body frame by this, and we get this extra term which corresponds to the gyroscopic effects. And simply we get this, in the end, this final structure that corresponds to the governing equation that would have some torques applied to a rigid body, and in the end would output for us the angular velocity and the rotation. Okay, so this is the dynamic model we are interested in, to model one rigid body that's only rotating in its place. Again, what we have here is an element of SO3. It's a integration in some sense, or it's the time derivative of it is an element of the tangent space, and this is mapped by the Lie group structure of SO3 to an element of the algebra. And this element of the algebra is nothing else than a skew-symmetric form of some free vector that we call the angular velocity. And when we represent this angular velocity in the body frame, and we represent the moment of inertia in the body frame, then the multiplication of these two together will give us the angular momentum. And the angular momentum, I can integrate it from the rate of change of the angular momentum, and I have the sum, or like the difference between the total applied torques and this cross-coupling term between the angular velocity and the momentum. Okay? And this was this term that we derived last time. And there are many different ways we can write this term. And usually people, again, depending on how you write it, the equations get different names because they were derived in different ways. We're going to look at it, not today, but maybe at a later stage. I'll tell you these names, what are they called. But for now, I can rewrite it in another form like this. Okay, so what happened from this slide to that slide is that instead of this was omega tilde p, I can make this p tilde omega. Okay. What is the relation that we used here? That the cross product of x and y is equal to minus the cross product of y and x. Okay. This is exactly the same. So this minus becomes simply a plus. Okay. The nice thing about this, this has a very deep meaning. We're going to look at it later when we talk about stability. But for now, it's just one form of another form of the equation. There's even a third form, which we can use this equation and completely eliminate the momentum simply by writing it like this. And what we just did is that all the equations in terms of the momentum, I wrote them in terms of j omega. And yeah, we have just one differential equation in omega and another differential equation in terms of r. And this is the rate of change of orientation is equal to some nonlinear function of the angular velocity, and the rate of change of the angular velocity is equal to some nonlinear equation of the angular velocity again. So you see, this is the nice thing about writing the equations in the body frame, because this is the equation of r. So this is a differential equation of r and omega, but this is a differential equation of only omega. Okay, so this is a nice thing. Okay, any other question?
This omega, this p omega and the body frame.
That's what I just said. So when we write it in the body frame, then we don't have that the moment of inertia is depending on the rotation matrix. It becomes a constant. The moment of inertia is a constant tensor only in the body frame. If you would start to represent it in any other frame, then it becomes depending on the orientation. Can we easily go to the case of rigid body motion? Yes and no. So the easy thing is that everything we did, we're going to follow exactly the same. We're going to have a 6-dimensional object that would correspond to torques and forces in one thing, just like when twists was the combined angular velocity and linear velocity. Then this new object we're going to be calling a wrench is the combined force and torque. Kinetic energy is again half V transpose. Again, this is the V as in the capital V, the script V, the curly V. So this is the twist variable. So half V transpose. And this is the generalized inertia tensor, which again will have some sort of, it will take the mass and also the angular momentum, the moment of inertia, making them into a 6-dimensional object, 6x6 object. It's also a function of h depending on which frame that you look at, similar to what we had with the r. It's too much. Oh, what happened? Okay, so this is half V transpose IV. We take the gradient with respect to the we take the gradient with respect to the kinetic energy with respect to the twist. We get the generalized momentum, which is again a combination of linear momentum and angular momentum in the same way. And the Newton-Euler law, the combination of Newton's law for the translation and Euler's law for the rotation, is simply the rate of change of the generalized momentum is equal to the total applied wrenches, provided you're looking from a stationary frame. Everything is the same. So this is the easy part. The hard part is that you can no longer think of wrenches and momenta as vectors. And this is where linear algebra really breaks down. Okay? Because, and this is, again, I can speak about this for a while, but the fact that you have something called vectors and covectors is completely overlooked in many books and many fields of study. Okay, and people usually write vectors and usually write covectors as vectors, and then you don't know what's the nature, because both of them can be written as an n-tuple, as some numbers below each other. You're going to be see clearly here that we can no longer do that. The way we're going to be differentiating between what's known as a vector and what's known as a covector simply by how they change, how they transform under coordinate changes. And we're going to be seeing this, okay, from a very like a very intuitive way. Energy, or in this case the kinetic energy, is a scalar, which means that looking at or calculating the kinetic energy from the B frame or from the S frame or any third frame should be equal, right? So no matter which frame I'm looking at, kinetic energy should always be the same because it's a scalar quantity. It doesn't depend on coordinates. So now let's take a look at specifically the kinetic energy of the twist in the B frame. And we have this nice equation. You see, in general, the kinetic energy is a function of H and the twist. But when we look at it in the B frame, it's no longer depending on the homogeneous transformation. Why? Because the inertia tensor, the generalized inertia tensor, becomes a constant. This is the general form of the generalized inertia tensor, and it's a 6x6 matrix. So this is its matrix representation. In the top left corner, it's a 3x3 moment of inertia matrix or tensor. In the bottom right, we have a 3x3 identity matrix multiplied by m. So it's like m 3 times, one in the x and one in the y and one in the z direction. They're both the same number. But on the diagonal term, we have something that depends on where is the location of the center of mass in the frame that you chose. So I can choose the frame B to be anywhere. The only condition is that it should be fixed with the body. So whenever the body rotates, it should rotate with it. Whenever the body translates, it should translate with it. But should it be at the center of mass or not, in general, I can choose it in the way I want. Where is the actual center of mass located in this reference frame gives this cross term. If you choose smartly, if you know where the center of mass is and you choose to put the body fixed frame at the center of mass, what happens to this term is that it becomes 0 because the center of mass becomes at the origin of the B frame. So you just get a 0 here. So this becomes a 3x3 matrix, and this becomes a 3x3 matrix. It's still not a diagonal matrix. You still need to do something else before this becomes a diagonal. You need to choose that the B frame is at the center of mass, but also aligned in a certain way such that it matches with the principal axis of inertia. And this is something that is physically, it's something that's physically you can calculate from any CAD model or depending on the shape of the body you're talking about. So this is a generalized inertia. And this is how it looks like when we calculate the kinetic energy in the B frame. Just by playing around with what the variables we introduced, we can see that twice the kinetic energy is nothing else than the momentum, the generalized momentum transpose multiplied by the twist. Everyone agrees? Does this ring a bell? Did we discuss something like this before? What was it? No? A joint, yeah. Something related to the wrench. You remember when we discussed about vectors and covectors a long time ago when we were talking about abstractly? We said that covectors can be considered as a map that would eat a vector and give you what? A real number, right? A scalar. So this is a vector, you all agree? And the momentum is something that would eat it such that it gives us a scalar. So you can see immediately now that momentum is a covector from that perspective. And you can also see that that the twist itself is also a map that would eat that covector and give us a scalar number. Okay? So go back to this part when we talked about tensors and we talked about how vectors and covectors are actually mapped from V and V star to R. This is something related to it. But even if you didn't get that part, no problem. Kinetic energy is invariant. So we said that no matter which frame we look at it from, we should get the same number. So if I represent the twist in the from the B frame to the twist in the S frame, I can use the adjoint transformation. And simply because this is the add H, I can transpose it and get it inside here. Okay, you all remember, you all know that the X, so A, if you have a matrix A multiplied by a vector X, and you take the transpose of both is equal to X transpose A transpose, right? So this is precisely what we did here with the simple linear algebra identity. And what you see inside of here is the thing that will be paired with the twist seen in the S frame to give us a scalar, which is nothing else than the momentum in the S frame. And you see clearly here that if I have the twist in the B frame and I want to transform it to the S frame, I multiply it by the adjoint from B to S. But if I have the momentum in the B frame and I want to transform it to the momentum in the S frame, I have to multiply by the inverse of the transpose of the adjoint. And the inverse, again, a property now, that's a property, is that does this adjoint transformation, does it have that the property that its inverse is its transpose? We don't have that. Okay, you can check it out in the math, it doesn't work. So, and this is the picture you can always keep it in mind. If I go from B to S by the adjoint, I always need to come back from S to B by the adjoint transpose, which means if going from here to here by the transpose of the adjoint, then I can go from here to here by the adjoint transpose inverse. Why have you never seen something like this before? The answer is very easy. When we had the same holds for forces, velocities, torques, and angular velocities. When we have forces and velocities and linear velocity, then twice of the kinetic energy is also equal to the momentum, linear momentum multiplied by the linear velocity. When I change coordinates, how do I change coordinates from frame B to frame S with a linear velocity? I multiply it by a rotation matrix. So when we look here to go from a linear velocity from the B frame to the S frame, I multiply by R. When I go with the momentum, I go by R inverse transpose, which is R. When we do the same with the torques, then I transform torques by R, and I transform the twist by R, and I transform the torques or the angular momentum by R transpose inverse, which is same R. When we do the same, one second. When we do the same with the wrenches, and the wrenches is the combination of of torques and forces, and the pairing between this wrench and the twist will always have a unit of power, because I'm gonna take the between quotes the inner product. That's completely wrong, but again, just the duality product, properly speaking, between the between the torque and the angular velocity part here, and between the force and the linear velocity part here, which will give us in the end units of mechanical power. You all know that torque multiplied by omega is power, and force multiplied by linear velocity is also power. So this will be just the total power of this body moving around. And again, just play the same trick. Try to look at the power from the B frame and from the S frame. You're going to find that twists change coordinates in this way, while wrenches change coordinates in that way, which means that they are not the same object. They don't live in the same space. We cannot treat them in the same way. This is known as a vector. This is known as a covector. So twists belong to R6, while wrenches and momenta, generalized momenta, because they are in a different space, even though there are 6 numbers. We write them as 6, whatever you call a vector, right? But they cannot be the same space. We cannot call this a vector space and this the same vector space. That's why we call this the vector space R6, and this is the dual space to R6, which maps wrenches and generalized momenta to each other. Is that the other question?
not diagonal, we need to be aligned with the principal axis.
Yes.
This is only regarding JB in the body frame, right? To have only 3 elements instead of the 6 elements.
Yeah, that's right. And also when you place it at the center of mass, these two get zeros. So you have this completely diagonal matrix. Yeah, you have to be aligned and you have to be at the center of mass. Yes, that's right.
Difference between a vector space and a covector space. In what is the difference? Like in the end, I get 6 numbers.
Yes, you write them as 6 numbers. You write them as a 6 tuple, but they're different spaces. Yeah. Different spaces. I cannot say that they are the same. I cannot say that this lives in the same, this quantity lives in the same quantity as this. I cannot say that. Okay, because they change coordinates differently, and this is the big issue. They change coordinates differently. This is the key word. Okay. That's true. That's it. That's correct. Yeah. This is actually how wrenches are introduced. Yeah, that's correct. Yeah. And that's why another also thing that you can get an insight that you can get out of this. I can never equate two things except if they are in the same space, right? I cannot say that I have something that's a vector and equal to something that's a covector. And this is another proof that actually wrenches are equal to the rate of change of momentum, because momentum is also a covector. So this is another proof that equality here is correct. You can never have something that says wrench is equal to some velocity. You don't have that. We have something similar. We have here that wrench, or a covector, which is the generalized momentum, is equal to the inertia tensor multiplied by the vector, which is the twist. So I do have an equality here, but this is where the inertia comes into place. The inertia, you can see it as a map that eats a vector and gives you a covector. And that's why the inertia tensor, even though it's a 6x6 matrix, it's not a linear map. It's what we introduced a long time ago as a bilinear map. It's something that eats 2 twists and gives you 1 number. Where do you see that? You see it immediately here. The inertia tensor, I need to give it 2 vectors, not 2 covectors. I need to give it 2 vectors so that it gives me a number. This is its nature. And that's why if you look how the inertia tensor changes coordinates, you're going to find it's a different if we had a change of coordinates of linear maps. Okay? So again, that's a lot of wording, but you need some time to just digest it. Question?
For example, we have an abstract quantity we don't know anything about, whether the properties or what space it's existing. If we're able to recognize its quote-unquote vector, we're able to prove it mathematically that the inverse, the transport of the inverse is the required map to get from a particular frame to another, then we reach the conclusion that that particular quantity is actually a covector of the initial vector.
That is true. But again, simply you can say that if you have 2 quantities, okay, if you want to check whether 2 quantities belong in the same space, they have to change coordinates differently. That's the key word. Okay? So if you have a vector, okay, and another, so if you have a twist and I give you something that's new, right, so a 6-dimensional number, and I tell you change the coordinate of the twist, how does it look like, and change the coordinates of this new 6 tuple, and if they change with the adjoint matrix, they are both vectors. If not, they are not the same. You need to introduce a new space. Okay? Let's take all of this information and go back to the rigid body dynamics. We didn't finish it last time because of this missing information. We didn't know how do we transform the momentum from one frame to the other. Now we know how to do that. And simply, the equation becomes like this. Everything here is exactly the same structure, nothing new compared to the rigid body rotation and the rigid body motion, because instead of SO3, we have SE3. That's the only thing that changed. Instead of having 3x3 matrices, we have 4x4 matrices. Instead of having 3-dimensional vector proxies of the tilde form, we have 6-dimensional proxies of the tilde form. So this is how the structure looks like. We have the kinematic relation between the twist and the rate of change of the pose or the homogeneous transformation. We have the rate of change of the momentum in the stationary frame, of the generalized momentum in the stationary frame is equal to the total wrenches applied to the body expressed in the S frame, and we have this relation between momentum and the twist. Now, again, the same exercise we did last time, you're gonna have a nice homework exercise to prove it yourself. We can write that the generalized momentum in the body frame looks like this. And we get here an extra term. This is precisely the same as the extra term we got for the gyroscopic effects, but now you can consider it will be the gyroscopic effects plus some extra term that will couple rotation and translation. This extra term is precisely what you know as the Coriolis forces. So Coriolis forces are precisely, will come in this term here. This term here, again, I just write it like this. It's also a nonlinear function. It's a coupling between the twist and the momentum. Just like if you go back to the angular momentum and the angular velocity, you're going to find we had some coupling between both in this box. The precise map of this, we call it the adjoint operator, okay, of the algebra. You're going to be deriving it yourself, and you're going to see it in the homework. I can play around with the matrices or use some deep insight to rewrite this. We can rewrite it as, instead of a function or like a map of the twist multiplied by the momentum, I can write it as a map of the momentum multiplied by the twist. And again, I can rewrite it as a map of the momentum like this. This has also a very nice property that actually this map is skew-symmetric. Again, more on this later. Just two forms of the equations. You're going to be proving them yourselves. And that's it. This is rigid body dynamics. So given the combined forces and torques together, which again make up the wrench, I go through this whole differential equation. Of course, it's a nonlinear differential equation. It's a nasty one, but in the end, I reach the pose and I reach the output. As an output, also I have the twist. Okay? So I have pose or position orientation, and I have the rate of change. Sorry, I have the twist, which includes the angular velocity and the linear velocity, and that's it. So this is our building block, which has forces and torques as an input, and pose and twist as an output. Okay? And we're done with the dynamic model. Easy? Easy, okay? Okay. Any questions? Yeah. No. So the question is this, where was it? Yeah. Is this adjoint a vector and this adjoint transpose is a covector? No. The adjoint is a map from R6 to R6. It's a linear map. And this is a map from the dual space of this side to the dual space of that side. Does anyone remember what was the name we introduced to this map? No. We give it a long time ago when we were talking about the abstract stuff. We said if I have a map, a linear map from one vector space to another vector space, which in this case is the same. And then I have a map from the dual to the dual. What did we call this map? We called it the dual of the linear map. And this is something, again, when you have a linear map, we can write it as a matrix. The dual of the linear map that we introduced a long time ago is nothing else than the transpose. But the transpose is not simply just one trick. Let's make the rows into columns and things are nice, right? Because what did we do when we write the transpose in this way? It has a very deep meaning. Because this is going from a vector space to a vector space, but this goes from a covector space to a covector space. Of course, if you have everything is, for example, this is R3 and this is R3 and this is R3 and this is R3, and they have here rotation matrices, then you consider it's the same, right? You don't differentiate between vectors and covectors. But in R6, it makes a big difference now. No. This is R6. This is R6. And this is a 6x6 matrix. Yeah. I can write this as a 4x4 matrix by putting in the tilde form in the way that we showed before. I can also write this in a tilde form. And I'm going to call this an element of SE3. And sometimes we call this the element of SE3 star. And S small SE3, right? Which is if this is the Lie algebra, we call this the dual Lie algebra. Okay? Again, this is off topic. Okay? If you want to dive into deep. Any questions again? Easy? Okay. So that's it with the dynamics. Now let's take a small, not a break, of course. No. There are no breaks here. No. Yeah, okay.
When we are dealing with this computationally, I mean, with computers, is it better for us to program this in R6 or should we program it in SE3?
Okay. Excellent question. Let's maybe this is too complicated, right? Let's take the easier version of it, which is this picture. This picture, okay? The excellent question is, let's maybe take that picture. Let's take this picture. The excellent question is the following. How do we simulate this? Given this equation, given this ODE, this is differential equation in time. Who took here a course on simulating differential equations, numerical methods, numerical analysis? Everyone took, right? Did you write code yourself to simulate any equation of motion? Transforming an x dot equal to f of x into something that's like xk plus 1 equal to x of k and xk minus 1 and xk minus 2, right? This is what, in the end, what the computer does, right? The computer in the end is just a big calculator. You need to program it. You cannot tell it, I have x dot equal to f of x. It doesn't understand continuous time. It understands only discrete time. So you need to write this equation. We need to transform this equation into discrete. And funny enough, the way long time ago in mathematics, you've been introduced to the integral and to the differentiation is actually by going from the discrete and taking the limit as the size goes to 0. And then at some point, I don't know, in engineering education, people lose this idea that actually integration and simply summation, and differentiation is simply just taking the difference between the last 2 points. And this is the whole idea. So how do we write this in the computer? You need to transform these ordinary differential equation to what's known as a difference equation. That's the first thing. Is this a linear difference equation? It's a nonlinear, of course, difference equation because it was a nonlinear ordinary differential equation. But there's even a bigger issue here, and it's very deep. The question is, let me just, actually, I wanted to make a whole lecture on it, but given the time and that's not the scope of the course, let me just give you a very small sketch of what are the problems that you face in 3 minutes. Okay. So whenever we say x dot, let's assume that x is an Rn. Or just R even. Let's stuck by R. So x is an R. And x dot, how do we define x dot? Exactly. So we define x dot or approximate x dot simply by saying that I have an x at a time t plus delta t minus x at time t divided by delta t, okay? This is precisely how we always derive x dot. And simply, if I have x dot and I want to calculate x, what do? I simply use this equation and I say, okay, x of t plus delta t is equal to delta t multiplied by x dot, because I have it, this is the input. And then I add the previous x that I had, okay? So next time step, and usually we can write this as, again, let's assume that x of t, I'm gonna write it as x small t, or some, and now we don't use time because we were talking about like steps. We use just like, again, some index, we use it k, and this is simply xk plus 1. And in general, actually, you have this, you can always add like, this is, if this is kt plus delta x and this is kt, you always have this scenario. I can always go from one time step to the next by this equation. So in the end, the difference equation from going from here to here is simply xk plus 1 is equal to xk plus delta t x dot, and the x dot is like the velocity, right, that I'm going to have as an input. And this is simply what you put in the computer. Easy, right? Makes sense. Can we generalize this to a function of x? Yeah, of course, you can always do that. You can use the implicit midpoint. You can use the Runge-Kutta. Again, I'm pretty sure you learned about this stuff, depending on who taught it to you. Maybe you hate it or you like it. But again, so this is how you usually write ODEs into computer code. That's the very simple thing. I have R that lives in SO3. And R dot, how is it defined? Play the same trick. It's approximately R, what we called K plus 1, minus RK divided by delta T, which means RK plus 1 is equal to, again, RK plus multiply by the R dot. What is the R dot? Again, it's like RK multiplied by omega tilde. right? At time k, can do that. That's it. Very easy. What's wrong with this? Absolutely. Is the summation or the difference between two rotation matrix a rotation matrix? Why? What is missing here for SO3 so that we can make this operation? What structure it doesn't have so that we cannot? What was it called? No. Again, yeah. What was the space that what was the space that has this summation called? Vector space, exactly. So SO3 is not a vector space. I cannot do this in a vector space. It's a Lie group. So I cannot do this on a Lie group. And try this out. You're gonna get disasters results. Just simulating this rigid body rotating will actually diverge. It will explode. The simulation will explode. It will not work. How do people solve that? Again, you have many ways. First thing is to do a proper, okay, not to do a proper, use Euler angles. It's worse even than doing this. Okay, we got horrible stuff. Use quaternions. That works. Okay, but again, you need to take care of the geometry of what quaternions have. Because again, you're gonna be simulating 4 numbers. Remember, this is 9 numbers, right? This is 9 numbers, and this is 9 numbers, and this is 9 numbers. So again, I need to be careful here. The way to do it is to design the integrator using the group structure, the Lie group structure of SO3 that it has, okay? And the whole idea is that I cannot take this difference at the point level, but there is something at the Lie group level that has this vector space structure. What was it called? What is something that's special about the Lie group that I can do pluses and minuses because it has a vector space structure? The tangent space, exactly. And there was a very special tangent space. Which one was that? The identity, which was the Lie algebra. So what people do is that do this at the algebra level, and then take whatever map. You remember how we mapped from the algebra to back? You use the Lie group structure. And these are just called geometric integrators. And in general, this is known as structure-preserving discretization, okay? Or structure-preserving numerical methods, okay? Because they preserve the structure of the underlying space. It's not enough just to assume everything is nice in R and everything in Rn. You get actual problems in code. Things blow up. Again, I have very nice stuff that I can show you here, again, in practice, but again, let's see where we go with the course.
For some reason that we map this down to the Lie algebra, perform everything on the Lie algebra, then take it back to this.
Absolutely, yeah. And by doing that, we make sure that whatever we get out, again, the whole keyword is this. Can you prove that whatever I get RK plus 1 here belongs to SO3? That's the big question. What was the condition that I give you 9 numbers and they belong to SO3? What? The determinant should be equal to what? What do you mean by plus 1 at the computer level? It means exactly 1. So if I take the determinant of R minus 1, what should I get? Machine precision 0, right? I should get 0.00000 10 to the minus 14, okay? And some machine noise, right? In the end, some noise because of it that actually we're not representing numbers precisely in the computer. That's the only thing I should get. I should not get not 0.1 time, not 1 times 10 to minus 6, not 7, not 8, not 9. I should get machine precision 0. So this is the difference between an integrator that uses the geometric structure and one that's not. But there's even more to it. It's more interesting than that. Let's go back. Yeah, let's take this guy. If I do an integration on the computer and I don't apply any external wrenches, what do I expect of the generalized momentum? Should be equal to what? The P dot should be equal to what? To be 0. So if I start with some initial momentum, what should this number be throughout the whole simulation? Constant, right? If I start with some initial rotation, for example, and some motion, this body should like drift around without changing this momentum, okay? And this is precisely what we know as the conservation of momentum law. It's a physical law that we assume. This is how we derive the equations. If you run a simulation in the computer and you don't have conservation of momentum, it could be because of these numerical artifacts that you assume you have some Rn structure, but you actually don't, and you get garbage in, garbage out. You wrote a simulation, you assume that this is a physical rigid body that's rotating, but that's not the case. Okay? And again, now we can not just preserve the SO3 structure, we can also preserve the physics that's there. Again, big topic. Again, this was 10 minutes off course. Again, we can have one whole course on it if you're interested. But for now, let's go back to question. Not on this topic, okay? Another question, okay? Yeah. How are you going to do? Okay, that's a very good point. How are you going to do the project? You're going to do it with the rubbish integrator, okay? Okay. Again, the integrators. Oh, that's a. Okay, let's see. What is the limit where these integrators, these bad integrators, perform very nicely as the nice integrators? Where does it really, or in other words, where do these nice integrators, these geometric integrators really shine? Is in this part. Okay. Have you ever had this scenario where you make the time step very, very, very small so that the simulation just works? Okay. This is precisely not a problem of the simulation, not a problem of your computer, simply a problem of the algorithm you use for the discretization. The nice thing about these geometric operations is that I can make delta t very big, and it would work very nicely. Some people that use this kind of geometric integrators, they use it for celestial mechanics, or just planets, and they're trying to simulate like 1 million or 1 billion time steps because they want to see what will happen and how this planet is revolving around this galaxy and around this sun for like 10,000 years or one, no matter what number they're using. Okay, so I have a very, very long time step. When we're doing robotics, we just have simulation of 1 second and let's stop it. Okay, or 10 seconds or 20 seconds. Something like this that's very interesting if you're doing learning with the simulations. You need actually that the simulation is physics because we're going to use this simulation. We're going to be going to the real life, and this is known as the sim to real gap. Again, I'm going to stop talking because I like this topic a lot. Like I did some research in it, but again, so let's go back. What I want to end this topic with, okay, inshallah, in the last 30 minutes is that let's take the information that we know, only what we know so far, and try to look at some robotics part again. So shift from the math, go to some robotics so that you don't sleep during the course. So let's see, where does this go? Nope. Okay. So what we know so far is how do we model rigid bodies, and if we have only this information, can we model something, an actual robot that's already out there? The answer is yes. You can model what are known as multi-rotor aerial vehicles, right? UAVs that are propelled simply by propellers, okay? So they use propellers for actuation, okay? This is different from, for example, flapping wing UAVs that use flapping to like bird-like or like insect-like UAVs. This is different from fixed wing UAVs like these, I don't know, like, I lost the name of it. The Predator, for example, this famous Predator UAV. Again, all of these are different types of drones, but this type of drone is very unique in the fact that we can model it simply by just one rigid body. If you know how to model one rigid body, you can write the dynamic equation of this, and you can start doing stuff, right? Do control, do planning, and whatever you wish. These are very popular because they have very, very simple mechanical structure. So, and actually you need to know very little about aerodynamics to be able to model this. It's very easy. And everything in trying to relate, to write this dynamic model, you already know, which is simply the equations that govern one rigid body, and how do we represent wrenches, and how do we write wrench from one frame to the other. And this is only the tools we're going to be using to model these kind of robots. There are different classes of robots. So you have, for example, the quad-rotor and the hexa-rotor. This is a class that's known as under-actuated multi-rotor UAVs. These are called fully actuated UAVs, but they don't have any moving parts. And these are fully actuated UAVs that actually have propellers that are being actively tilted. So these are like fixed tilt, fully actuated UAVs. And these are variable tilt, fully actuated UAVs. And these are under-actuated. Who here is familiar with this term, under-actuated and fully actuated? What does it mean? Okay. How many degrees of freedom does a rigid body have? 6. So how many propellers do I need? So a quad rotor is underactivated or fully activated? Underactivated. A hexarotor, is it fully activated or underactivated? So who says fully and who says under? Who says fully? 6 propellers and 6 degrees of freedom, right? Who says fully? Okay, I don't see the hands. Okay. 1, 2, 3. Who says underactivated? Okay. And the rest of the people are undecided. Okay. It's underactivated. So how do we know that? Is there a way in math that we can see whether it's actually underactivated or fully activated? What we're going to be doing is the following. Each one of these propellers that's already out there, it produces a wrench. Okay? It doesn't produce a thrust, it produces a wrench. It doesn't produce a force, it produces a force and the torque. Okay? Each one of these propellers produces on the rigid body, on the drone itself, on the drone body, a force and a torque. But this is in like a force and a torque at a distance. Okay, we need to transform all of these forces and torques where? To the center of mass, right? To the body frame, right? To have a frame that's fixed with the body. And we combine all of these together. And in the end, we just have one total wrench, okay? Which is what we use for control. So, because if I know this wrench, again, if I can change this wrench, then this is the input that I have for the drone, and I can start to do control and design controllers and make this drone go where I want and so on. The map between the individual rotor thrust and the control wrench in the end applied on the drone that's attached to frame B, expressed in the frame B, is given by a map. What's the dimension of this map? 6 by?
Depends on the configuration.
Depends on the config. It depends. The dimension itself depends only on what? The number of propellers, exactly. How many propellers do you have attached to this rigid body, which is the drone in the end? So, for example, the quadrotor has 4 propellers, so the lambda here will be a 4 vector. The hexarotor has 6 propellers, so lambda here will be a 6 vector. This Volero, for example, drone has 6 propellers, but each propeller actually can be tilted, can be varied. So this is, in this case, we're going to have a mapping that will be time varying, because again, depends on this angles in between, and it will map 6 propellers that I have. I can change their thrusts. So this mapping, okay, this is known as the control allocation matrix. Okay? It has different names. Control allocation matrix is one of them. Distribution matrix is another one. Mixing matrix, again, different names for the same thing. So the dimension of this M is simply 6 by the number of propellers that you have. And based on how this M looks like, now you can classify whether this is an underactivated, a fully activated, or an overactivated probe. Usually, how do people control of drones? Okay, this is like a standard way of not standard. I would say a very common way of doing control of multi-rotary aerial vehicles is that we design a controller only assuming that we have the wrench applied on the body. Okay, so I assume that I have one rigid body. What is the input and what is the output? The input is a wrench that comes from the propellers. And then I have as an output the homogeneous transformation, the pose, and the twist. And then I feed those back by some sensor, again, which is not part of this course, details about it. But I feed them back by some sort of sensing or some estimation algorithm. And then I would design the controller assuming that I can apply this wrench to the body. Of course, I cannot apply this wrench directly. I can apply what? The individual motor thrust. So if I know what this should be, what should I do? I should inverse this relation. Of course, if this is a map if this is a 6 by 6 matrix, can I always invert it? Yeah. If its determinant is not 0, exactly. It has to be like invertible matrix. So if this is invertible, then we call this a fully activated drone. Okay? If it's not invertible, then I have to check. Okay, if I have, for example, if its rank is less than 6, then we call this an underactivated. And if its rank is, if its raw rank is, if it has a rank of 6 but more propellers now, this becomes overactivated. This is precisely what you had again, in linear algebra as what's known as the underdetermined system and an overdetermined system. Again, we're just trying to solve a linear map here. And this is known as the control allocation problem. And again, you can do a whole research on how do we actually solve this problem and how do we implement it in code, how do we do it as fast as possible, and again, a lot of details. Yeah.
What's the result of the range?
No. Okay, this is actually what we're going to be doing now. Okay, so let's start. So let's go to the board. Let's write some stuff on this. Okay. So the first thing that we need to do, and again, this is exactly the same thing you're going to also do when you start working in the project, is what? Modeling. But before modeling, yeah?
That your drone applies the frames.
Frames, exactly. The first thing that you have to do, what are your frames? This is a choice. Your robot, your model, your frames. So in our case, let's take, for example, this is a very elementary 3D view of a drone that looks like this. Okay. And again, you can have many propellers. Okay, so this is one propeller. This is N propeller. Okay, you can have many of these. So this is the ith propeller. Let's maybe go a little bit down. And now let's put the frames. The way we're going to be putting the frames is as follows. We're going to choose that this is XB hat, and which is like the forward of the drone, and the YB hat is the left of the drone, and then we have that the Z is up, okay? And again, this is what you define on the robot itself. So whenever you have a drone, of course, the drone itself doesn't have any forward, because with multi-rotors, you don't have like a shape like with airplanes, for example, that has to move in this way. So it can move sideways and it can move in every direction in general. So we don't have this forward from the structure. You have to choose it. This is my structure. This is my forward. So this is the B frame. And we're going to have another frame here, which is the propeller frame or the ith propeller frame. We're going to choose it as follows. We're going to align the Z P sub I frame with the direction where thrust is produced. So this is the direction where thrust is produced. So propellers, when you rotate them, like for example, in this direction, okay, they produce thrust with the right-hand rule. Okay, they produce thrust in this way. And so this is the first choice we're going to make. The other choice is that we're going to be choosing the X frame, or the X direction, the XPI direction, to be aligned with this direction, okay? Okay. So that if I am at the origin of the B frame, of the body fixed frame, and I just take a line to the origin of the PI frame, okay, I'm just collinear with that line. This is the XP frame, and then the YP frame will be perpendicular to this plane, okay? And you see, because we're using orthonormal frames, I don't need to write 3 frames. It's just 2 is enough, and the third one you can always deduce mentally, okay? Easy? Okay. So this is the choice of the frames that we have. And with this choice, each one of the propellers, or at least the direction of the propellers, I need to provide 5 pieces of information, okay? In general, what we have is the following. We have that this is a choice that I already made, because this depends on the configuration of the robot itself, of the propellers. I have HPI with respect to B is simply the pair of RPI with respect to B and the psi PI with respect to B. So this is your choice, okay? Based on how big is the drone, where is the rotors located, how many rotors, you're going to have many of these homogeneous transformations. And again, this is the exact same thing you should start with. Choose your robot. Again, first, choose your team in the project. Choose your robot. I'm going to send precise instructions, but again, this is just an overview. Choose your team, choose whatever robot you have, and choose all of the, where are all of these frames. Whenever you have something that's interesting, a point where, for example, there's an end effector, there's a joint, there's something, put all of these frames there and give them names, and that's the first thing you do. How do you represent one frame with respect to the other? By homogeneous transformation. I write them like this, okay? But you know that it can be written as a 4x4 matrix in the normal way. The interesting thing here is that the rotation matrix, which is RPI, if I look at this direction, this is very important, okay? Because this is the ZPI hat. But I need to know what the ZPI hat looks like in the B frame. How do I do that? The rotation matrix, right? So if I multiply RPI B by ZPI hat, this is a vector. What do I get? I get the direction of where thrust is produced, seen from where? From the B frame, okay? Easy. We're going to be calling this variable UI, okay? Just for simplicity, because we're going to have this a lot. And we're going to be calling also this guy, we're going to be calling psi I, okay? Psi I is constant, so it doesn't change with time. So where this propeller is located on the drone doesn't change. Okay, so we're not considering drones, for example, that have any prismatic joints or like are moving around or something. We don't have that. While the orientation can change, right? Okay, because it depends, for example, if you have here some extra actuator that maybe will tilt the propeller in this direction, right? So it can tilt the propeller in this way. So in general, this rotation matrix will be a function of time, and this UI will also be a function of time. Variable pitch, yeah, exactly. But also, again, so take this scenario, for example. If I always want XP hat to be in this direction, how many left degrees of freedom can I rotate around? Actively. I can do this rotation, right, with a motor, and I can also do what? This rotation with a motor. Everyone visualizes it? Okay, so if you have a propeller that's attached like this, I can have some extra motor that makes it rotate like this. Okay, so let's maybe draw a circle. Let's see. So I can have an extra propeller that would rotate in this around this axis, which is around the XPI axis. Okay, so I can actively tilt the propeller in this way. I can also actively tilt it in that way, right? But I'm not considering actively rotating the propeller around the Z direction, right? Because it will be completely useless. Okay? You all imagine that? So in the end, where the propeller is located, I only need 5 pieces of information. I need these 3, which are constant, and I need 2 of these, okay? Because I'm only looking at the third one, okay? Because I'm not changing that. Yep.
For example, it's something that's supposed to be controlled by a remote, or maybe it's performing an autonomous mission by
Off topic. That's off topic for now. Let's look at the modeling part. Don't focus on the control part. Just focus on describing how things change velocities with each other and positions, right? Which is the kinematics part. We're only, again, doing at this level first. We're gonna do something that we didn't do before, because this, when doing it here, it becomes very easy. We're gonna simplify, and we're gonna have this intuitive way of describing the rotation matrices. We're gonna, for the first time, parameterize this by 3 angles. Okay? We're gonna parameterize this rotation matrix by 3 angles. Okay. What is the choice of the angles? Yeah.
Since we want to fix the X, so we can only rotate the rotor around X alone.
Actively, yes. Yeah. Actively, you can rotate around X. You can actively rotate around Y. Okay. But you cannot actively rotate around the Z.
If I rotate around Y, I can change the direction of the X.
Yeah, exactly. So you're going to do something like this.
Then it will not be aligned anymore to the B, the way we want.
That's a good point. Yeah. When this angle is 0, it's aligned. Otherwise, it's not. That's a good point. Yeah, that's right. So it's on at when the angle around which you're rotating here is 0, then they become aligned. So this is like the reference that you have for the 0. That's a good point. So RPI with respect to B as a function of time, we're gonna parameterize it as follows: as some rotation by an angle psi I around the Z, another rotation around the Y of some beta, and another rotation around the X by some alpha. Okay. This is constant. This is a function of time, and this is a function of time. We're going to be calling the cant angle. This will be called the dihedral angle. And this will be called the heading. Okay. This is the first time we chose to represent the rotation matrix by 3 consecutive rotations, or by Euler angles. Okay. You remember I always told you don't do that. Why are we doing it here? What?
Because the rotation is limited. We don't need full 36 degree to rotate the drone.
Maybe that's okay. That the rotation is limited, right? We only need some angles. That's okay.
There is some singularities.
Okay, good point. Yeah. So the short answer is the following. We're going to only use these angles to represent the R matrix, not the rate of change of the R. So we're not going to do any velocities with these angles. We're going to only represent them with the R. Going back and forth between these guys and the R is okay. Going back between the rate of change of R, or the rate of change of these angles, and the angular velocity, this is where singularities happen. Okay? So this is the short answer. If you already know what I'm talking about, it makes sense. If not, just take it as one way of writing the rotation matrix. These have physical meaning. The heading is simply the following. If I have, this is the B frame, okay, that looks like this, and then I take this frame and I place the robot, place the propeller like that. This, you see, I changed the heading, right? So this rotation means the heading. Then if I go here and then I start rotating the propeller like this, which is around the X, we call this the cant angle. If I rotate around the Y, we call this the dihedral angle. Okay, so these are actually physical angles to describe this orientation in the end we're interested in. Okay. Now, let's do the following. If I have just this propeller, and then I have the ZPI frame, this is the XPI axis, sorry, and this is the YPI hat axis. The wrench that's applied by the propeller on the body of the drone itself, expressed in the PI frame, is given only by 2 numbers. It has the following structure. It has the wrench applied by the ith propeller, and it's applied on the body that's attached to the B frame, which is the drone itself, the drone structure, and expressed in the PI frame. Okay, so this is the PI propeller, okay, or the wrench, like the aerodynamic wrench. Okay, let's maybe write it like that. So this is the aerodynamic wrench that comes from the ith propeller applied on the body attached to the B frame, expressed in the PI frame, is simply 3 torques and 3 forces. So 3 torques, T1, T2, T3, and then F1, F2, F3. And again, this 1, 2, 3 are simply torque around this axis, torque around that axis, torque around this axis, force around this axis, sorry, force in this direction, force in that direction, and force in that direction. So these are the numbers what they have. That's why you can simply just call them Tx, Ty, Tz, and Fx, Fy, and Fz. Okay. Anyone who did, I don't know, quadrotor modeling before, does anyone know which one of these is zero and which one is given by some variable? Fz is not zero, okay? So this is a variable. We're going to be calling the force produced by the propeller in its own frame along this direction Z hat, we're going to be calling it the thrust. Does it produce any forces in the X and Y direction? Okay, for now, let's say no. What about the torque around the X and the Y and the Z? It has a torque around the Z, exactly. It's the reaction torque, precisely. So whenever you rotate a propeller, you always have a reaction torque because of the drag. Yeah. This reaction torque can be positive or negative, by the way. That's why when you have propellers, people who work with drones before, usually you have propellers that are put, one is counterclockwise and one is clockwise. One is counterclockwise, one is counterclockwise, so that you can have these different directions of the reaction torques so that they can usually cancel out and you don't need to like spend money with control trying to cancel them out, like control effort. So we're going to have here, again, some sort of sigma I multiplied by a torque, but there's something that's a modeling assumption that's very valid, and you can show it in practice, that the drag torque that's produced is usually a constant, right, or a fraction that we're going to be calling a fraction gamma multiplied by the thrust itself. Okay. So in the end, we simply have that the wrench is given by this direction. You see, this is just a direction that says, okay, I have a thrust in this direction and I have a drag torque around the same direction. So let's just put these values. So I have the lambdas in this direction and I have the lambda C sigma I, lambda I around that direction. Of course, this is lambda I. So each propeller has a different thrust in this way and an accompanied drag torque that comes with.
So what is lambda? What is sigma?
Lambda is the thrust that's produced.
Gamma.
Gamma is the constant that when you multiply it by something that has force units, Newton, will give you Newton meter in the end. So something that it's the proportionality constant between the drag torque and the propeller thrust. And sigma is just a direction. So sigma I is a number either 1 or -1, okay? Depending on whether it's counterclockwise or clockwise. It's just a convention. Easy so far? Okay. Now, the next part is, I want to have the collection of all, which is the aerodynamic wrench, applied on the B frame, expressed in the B frame. But this is like the total wrench. How do I do that? I can simply sum all of the individual propeller wrenches from I equal 1 to I equal NP. And I'm going to sum all of the aerodynamic wrenches, which are the individual ones, applied on B. Can I do that? Is this a valid thing? Why? You need to use what? Why? Why do you need to use that joint here? You cannot sum, again, this wrench, which is in, for example, the wrench of propeller I, expressed in propeller, the wrench of propeller 1, expressed in propeller's 1 frame. Can I add it to a wrench of propeller 2 in propeller's 2 frame? Why doesn't it make sense? Because they don't live in the same space. They are numbers that are not represented in the same basis. I need to represent, if I ever do summation of wrenches, they all need to be in the same frame. If I also do summation of twists, they also need to be in the same frame. So I need to have this in the B frame. But I don't have this in the B frame, I have it in the PI frame. What do I do next? I know how to transform the wrench of the aerodynamics of the ith propeller applied on the body B in the PI frame, I can transform it by the transpose of the adjoint. Why? Because it's a covector. By a homogeneous transformation. Which one is that? It's PI up and B down. Okay. For this to work in terms of the indices, you remember when we said about indices that they cancel out? The transpose, you can think of it as changing the order of BI and B. Because B is down and PI is up, but this is transposed. So it's as if this is PI down and B up. So this is PI down and this is PI up, so they cancel out. So it makes sense. This is like how it works, how to make it reason in your mind. So this I have, it looks like that. And this homogeneous transformation is simply given by, again, if we go back, we're going to find that it's just a parameterization of something that are constant depending on where I place the rotor or what is the direction, what is the heading of it. If it has, for example, like a constant angle that I'm tilting about, or a constant dihedral or a constant cant, or a variable dihedral or a variable cant, or variable both, again, depends on the configuration that you have. And in the end, you can simply just collect all of these transformations. And you're going to have something that's huge that looks like, you can rewrite it in the end as something that looks like this. Okay. Okay. This will be your exercise at home. Okay. You're going to have some, okay. This is something you can actually program very easily. You just need to provide all of these angles, okay, depending on the configuration, and boom, it will give you the control allocation matrix for whatever configuration you dream of, okay? Whether it's variable tilt or fixed tilt and so on, okay?
So if it is a fixed propeller, so that means that all of these three parameters are fixed.
Absolutely. Exactly. Then there's a constant matrix, yes. If it's time varying, then one of them becomes time varying and so on. Yeah, exactly. Okay. So this is a direct case study of what you learned so far. This is the propeller wrench, the total wrench in the end applied from the propellers. I can, if I want to model a drone, then I have the dynamic equation of it, the rigid body motion, okay, the equation of motion of the rigid body. So I can simulate this. I have the wrench applied from each of the individual propellers. I just missing one piece of information for this to be a model of the drone. What is it? What extra force do I need to take into account when I'm gravity, exactly. When I'm modeling something that flies, I need to take into account the gravity force. Okay? But if you're modeling, for example, a space robot, then or a space like satellite, this is all what you need. So this is just enough. This is the aerodynamic wrench. This is the aerodynamic wrench. But this is a very simplified model of the aerodynamics. By the way, in practice, you don't actually have that these are zero. Okay. The first thing that you have in practice is that the propeller is not 100% aligned in this way. Okay. Sometimes when you're designing the propeller itself, there are some sort of like inherent like angles that are already there, like 1 degree or 2 degrees or 3 degrees that are just inevitable when you're designing this propeller, the structure itself. Which means that if you have here some components that are not zero, again, they will get multiplied into this huge matrix. And this is a nice way that you can actually play around with these small numbers and see how sensitive is your drone design to these small errors, right? Again, this is why this is just one way of, this is like a general way of getting this control allocation. What do you do with it? You can do a lot of very nice things, okay? For design, for optimization, for control allocation, this is a huge topic that you can work around. But this is the standard way, using only wrenches and that joint transpose. Okay. Easy? Okay, inshallah. Okay, let's stop here. Okay, if you have any questions, I'll take them, but